So what we have is that 1 over root 2 should be equivalent to root 2 over 2 because all I did was multiply by 1, so these should be the same thing, right? And if you get your calculator out and you put 1 divided by root 2 and you get the answer, you'll get the same thing as you get if you type in root 2 divided by 2. So who cares, right? Either way, it's the same answer. So here's the reason. Back in the day, before calculators, these things had to be done by hand. All right? So if you wanted to know what 1 over root 2 was by hand, first thing you would need to know is what root 2 is. You don't have a calculator. So root 2 would be one of those things that you've memorized because it comes up so much. You would have it memorized. You know, everyone back in the day before calculators knew that root 2 was approximately 1.414, something like that. It keeps going. It's irrational. There's no pattern to it. Just keeps changing, like pi. All right? So 1.41. And to do this computation, to figure out what this is, you would have to go old school division. You'd have to put the numerator in the box, and you'd have to put the denominator out here. And then you would go and try and figure out what this is. So you'd be like, okay, 1.414 doesn't go into 1, so I'm going to have to put a decimal and then look at it as how many times does 1.414 go into 10? What? No, can't use your calculator. 6 or so maybe? 7, 8? Okay, so do you see how that's kind of weird? Yes? Now, compare that to this. If you rationalize, the difference now is that when you do your division, what goes in the box? Root 2, which is 1.414, and what goes outside the box? 2. Now bring your decimal up. 2 doesn't go into 1. How many times does 2 go into 14? 7. And you could keep working this out, 7. It's much easier to work by hand if your denominator is not a root and your numerator is a root. That's the reason. That's the reason. So if you did this, you should get 7 here, and then multiply 7 times that, and then you should get a 0, and then do it again. You should get 7. You'll get the same answer. So do you see why this is more valuable if you don't have a calculator? But we do, so. So this is obsolete, in my opinion, which is why if you leave radicals in the denominator, there's nothing wrong with that. Well, no, because by the time I figured out why it was that way, I was beyond that math that it mattered in anymore. So, all right, we good? We finished that, didn't we? Now, it should have been x minus 1, right? I changed the problem on purpose. So let's now look at this. What if I just do a small little tweak to that, and I put x minus 1 over 4x squared minus 4x plus 3. Now I have, instead of a constant over an irreducible quadratic, I have a linear expression in x over an irreducible quadratic. What do you mean? As far as my completing of the square? Yes, the question is, do we need to do completing of the square? And we're not quite there yet. Let's see, do we need to do completing of the square? Well, so I've never shown you anything like this, all right? This is the first time you've seen this. I wouldn't expect that you just walk in here and be like, oh yeah, sure, we just do that, all right? So here's the standard procedure for this. And I'll put a little disclaimer here, a little star. There are different ways you can do this problem, all right? You might go to another, like a tutor, and they may do it a certain way. You might have a different calculus 2 instructor show you a different method. The way I'm showing it to you is just the way that I prefer. And I think it's kind of the coolest way to do it. All right, so check this out. Back in Cal 1, we knew that if you have a quadratic and you take its derivative, that's linear, right? So if you start out with something with x squared and you take its derivative, that's guaranteed to have an x in it. So we have linear over quadratic. So if I let u be the denominator, my numerator is linear. So maybe this is just a basic u substitution. But we're going to run into some problems, aren't we? If u is this, du is 8x minus 4. dx. Right? Now notice I put this in parentheses because there are two terms there, right? Now I have in the numerator two terms, right? Yeah? This is the fun part. Wouldn't it be awesome? I mean, just awesome if this was 8x minus 4? Wouldn't it? Like if that was 8x minus 4, wouldn't I be done? I would just have u on the bottom, derivatives right up top. I'd just do a basic u sub and I'd be happy, move on with my life. So right now what I'm going to do is I'm going to force the numerator to become 8x minus 4. You ready to see it happen? Here it goes. All right, what do I really want? I want 8x minus 4, right? 8x minus 4. I'm going to start with the x. Let me try and make 8x first. Am I allowed to do that? That's a 1, right? That's a 1 out there? Now, I'm going to leave this 8 in the denominator out here. I'm going to pass the 8 up here through. Okay? So my next line will read 1/8, and we can't drop that 1/8. It's still got to be out there. And then 8x minus 8. Yeah? 4x squared minus 4x plus 3 dx. Okay, I'm getting closer, right? I have 8x minus 8, but I need it to be 8x minus 4, right? Yeah? Now, there are two approaches to this. You can realize that this is minus 4 minus 4. Do you agree with that? This is minus 4 minus 4. Minus 8 is minus 4 minus 4. But I'm going to do it a little bit different because sometimes this number is not going to be nice. It'll be a fraction, and it doesn't work as clean. So let me do it this way. I really want minus 4, right? Really want minus 4? Almost like what we did with the completing of the square. Four x squared minus 4x plus 3 dx. So what do you think I'm going to replace that red with? Well, I want minus 4, right? So I'm going to say minus 4 plus 4 right here. Yeah? All these little weird hidden zeros that I'm forcing in here. So that becomes 1/8 integral. I've got 8x minus 4 plus 4 minus 8 all over 4x squared minus 4x plus 3 dx. I didn't write these in red, but everyone understands that's your 0 right there? Now, why would I do that?
Because now you can do du minus 4.
Yeah, if I let u be this, right, the derivative of it is right there, but hey, I've got this other crap here now, right? Why don't we just split this into two integrals? Right? So let me do that. Let me split this. This will be 1/8. The integral, what I'm going to do for my first one is 8x minus 4 over the denominator. And then the other integral, I'm still going to have the 1/8, right? That's the 1/8, has to go to both. Integral, and then I need to put these two numbers together, right? So I kind of grouped them up. I did these two over this, and I'm going to do these two over this, but those two over that is what? Negative 4 on top over 4x squared minus 4x plus 3 dx. And
So that's du.
yeah, 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx minus 1/2 integral of 1 over 4x squared minus 4x plus 3 dx. All I did here was just pull this negative 4 out, right? All right, we made it happen. We've got, if I let u now be this, right? If that's u, the derivative of it is right there, right? So that integral right here is just 1 over u du. And what's the antiderivative of 1 over u du? ln. So this answer for the first integral, I'm going to put it here, is 1/8, right, because that's this, natural log of the absolute value of what? U, which is 4x squared minus 4x plus 3. Yay, I've got that. Good, right? But you still have to deal with this. Do you recognize this? That's the problem we just did before this one. Forget the negative 1/2. Didn't I just give you that problem a second ago? And what did we have to do? Complete the square, blah, 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 all that crap that we had to do? Right? All those steps, you would have to do that here.
Is crap a curse word?
Crap is not a curse word. See, I'm adapting. I'm adapting. Yeah. So can we all...
You're allowed to have one F word that's not sexual.
Yeah, it surprises me what you can get away with these days with PG-13.
But it can't be sexual.
All right, I have minus 1/2, right, times... Now, I circled this because I want everyone to appreciate the amount of work that that would now require, right? But since we just did this problem in the previous one, we can just put the answer in here? Yeah. Which... root 2 over 4, arctangent, x minus 1/2 over 1 over root 2 plus c. Done. What do y'all think? That's a long, that would be a long problem, wouldn't it? Like if you had to start that from scratch, you first have to make that, you know, force the top to be what you want it to be. And the beauty of doing it this way is that once you've done this part, it's going to split into two integrals. The first one's going to be your 1 over u du. The second integral is going to be a constant over a quadratic that's irreducible. You'll always, that second integral will always be a constant over your irreducible quadratic, which you complete the square on and go to town. What do y'all think of that? That hidden zero? It's kind of cool. That 8 over 8 in the beginning? Kind of nice.
Would you want us to combine the negative 1/2?
Yeah, you make this like root 2 over 8. But again, I wouldn't take off on the test if you didn't do that. All right. Remember, this is all leading us up to being able to handle rational functions. Integrating rational functions. We can take care of a constant over a linear, constant over a repeated linear, constant over an quadratic without an x term, a constant over an irreducible quadratic, and a linear expression over an irreducible quadratic. We can handle all those. How about a linear over a repeated irreducible quadratic? So I have a linear expression. I have a quadratic. Now this one's missing the x term, but the point is that it's irreducible. I can't factor this. And then it's repeated because it's squared. When you see this, you do exactly what we just did. All right? So I'm going to let u be what's in the parentheses there. X squared plus 1. What's the derivative of that? 2x dx, right? I'd really like to force the numerator to be 2x. Right? 2x? That's it. Just 2x. So how can I force this to be a 2x instead of x? 2 over 2 on the outside. Pass the 2 through the top. Oh, still have a 1/2 out here. 2x plus 2, right? And then over x squared plus 1 quantity squared dx. Now I can split it right now. Do y'all see I don't need a hidden 0 on this one? Because I need 2x, right? I have 2x plus 2. I just don't want that 2 there, so I split it into two little integrals now. Don't forget the 1/2 though, it has to go with you. So that becomes 1/2 integral 2x over x squared plus 1 squared dx, and then plus a half integral of 2 over x squared plus 1 squared dx. How are we going to handle that first integral? This, I'm going to use this, right? Use x squared plus 1. du is 2x dx. That's a basic u sub. That's just going to be 1/2 integral. Let's go ahead and do it. That's just going to be 1/2, this one, 1/2 integral 1 over, because 2x dx is du, right? So that's just u squared on the bottom, du. With me? What's the antiderivative of 1 over u squared? Negative 1 over u, or negative u to the negative 1, however you want to look at it. I'm going to have to come back to this. I'm just going to continue this right here. This is equal to 1/2 times, I'm going to go a little slower, negative u to the negative 1. I'm not going to put plus c because I still have to do this one. This is going to be negative 1 over 2u squared. No, not u squared, just u. And then that's just negative 1 over 2, what was u? X squared plus 1. So you see, by making that basic u substitution and then kind of forcing this thing to happen, and you split it, one of those integrals became very trivial, right? Just a basic u sub, and we're done. The other integral is not so nice, all right? Are y'all ready to work on this one? So I'm going to erase the board, and we'll start with that one. Just remember, this is part of our answer. So I have 1/2 integral 2 over x squared plus 1 squared dx. And I'm just going to pull the 2 out. 2 hits the half, it's gone. That's where we are. All right, what do you want to do with that? If we do basic u sub, just don't write this down. But if we do this, then du is what? 2x dx. Do you see that derivative anywhere? It's not anywhere, is it? Well, what you're not allowed to do, okay, is you cannot put like 2x over 2x here. You can never have variables outside the integral. You can't force them in, and you can't take variables out. You can only take constants in and out. So we can't do that.
This one isn't 17, right?
This one is not 17. Damn, it's really close, though, right? Damn, they say damn on the radio. Come on. It's, you know, come on. That's right. They say damn in the Bible. Various Bibles, not just one. Yes. Uh-huh. Trig sub. That's going to be it. That's right. We're going to have to see this as the square root of x squared plus 1 to the 4th. Now look.